Welcome to Lesson 6, Ochem students, and what we're going to do in this video is answer the following question. When does a nucleophile act more like a base than a nucleophile? All right, and to start, what we're going to do first is give you a list of nucleophiles and talk briefly about what makes them either good nucleophiles or bad nucleophiles, and at the top of the list will be the very good ones. So these are very good nucleophiles, and this more or less is a summary, right? Because out in the real world there are more nucleophiles than what we're going to talk about here. But these are the standard ones that are discussed in organic chemistry. All right, and some of you may need a reminder about what R means. So this is just literally going to be a collection of atoms. Usually it'll be like an alkyl group of some type. It could be methyl, for example. But R groups are also composed of other kinds of atoms or functional groups. So other atoms or functional, and I will just abbreviate that, or functional groups. All right, now what makes these three nucleophiles be at the top of the list for goodness is the fact that they're relatively large, and even though they're carrying a formal charge of -1 on each of them, they're fairly large, and so the charge density is actually very, very small, because the additional electronegative, or the additional electronic charge is able to be distributed over a very large surface area, and that makes these nucleophiles, I have a term that I use for them, it makes them softer. All right, and it also makes them more selective. So they don't just rapidly want to chemically react, say, with a proton. So they're more selective, and they tend to work better with electrophiles that have a lot of structure around them and things like that, because they tend to react more with the electrophilic center than they do with protons that might be part of the structure that are also carrying partial positive charges. Now, we also have what we call good nucleophiles, and in this list we're going to have bromide, we're going to have hydroxide, although take that one with a grain of salt, because again, it's going to depend on the conditions in which you're using that. And then we're going to have RO-. So these would be like alkoxides. And all of these we've used in the laboratory, actually. All of them we've used in the laboratory. We have cyanide is another example, and then azide. These are the common ones you find in organic textbooks, and these are all good electrophiles. Now, as we taught, or excuse me, they're all good nucleophiles. Now, so in this category of goodness, I raised an issue about, okay, when we talked about hydroxide, how that could be depending on conditions. So let's just make a short list of what influences the nucleophilicity. One of the factors is going to be basicity. How strong a base is this thing? How much structure is around the atom that's carrying the extra electron pair? All right, and what type of solvent is the nucleophile actually dissolved in? I think these are the top three things, in my opinion. So how strong a base is it? How much structure is around it? And 3, what kind of solvent is it dissolved in? All 3 of these things are going to influence how good the electrophile is. Now, you're probably wondering right now, what's he mean by structure? So let's look at a quick example of that. I'm going to put it over here on the side of the board. If we're looking at hydroxide, all right, the only thing that it has attached to it is the hydrogen. So, and you can pick which of these electron pairs is going to form a bond with an electrophile, right? This thing doesn't have much structure, so let's just say it. It has not much structure in it. Now, if I pull down the RO minus and we define the R this way, so I'm going to say it's methoxide. All right. Now, by comparison to the hydroxide, this has got more structure around it, right? Because we have, not only is the O bonded to a carbon, which is bigger than a hydrogen, there are also 3 hydrogens on the carbon. So what that's going to do is it will put more limitations on the ability of a pair of electrons on this oxygen now to interact with an electrophile. And we can take this a step further. I'm going to change the color. We could have something like this, where we have an alkoxide, and now what we do is we put 3 methyl groups on this carbon. So this would be tertiary butoxide, T-butoxide. And now there is a tremendous amount of structure around this carbon that's bonded to the O minus. So this nucleophile now would have serious limitations. And what I mean by that is that this would be a stronger base in a reaction than a nucleophile. It's going to be more reactive with hydrogens that it bumps into than it will be with an electrophile. And the reason for that is because the oxygen with the negative charge is going to have trouble reaching an electrophilic center because you've got all of this structure around this central carbon here. You have a ton of structure around this. That makes this oxygen here with the negative charge is going to have a harder time getting to an electrophile. It will be bumping in and extracting hydrogens quite a bit more often. Now, as we go down our list over here, the next grouping will be fair nucleophiles. These are run-of-the-mill. And again, remember that we've got 3 factors here: the basicity of the nucleophile, the structure that is around the atom that has the unshared pair of electrons, and the solvent that the thing is dissolved in. The solvation can limit the movability of the nucleophile, the ability of the nucleophile to get to the electrophile. And for the fair ones, we're going to have like ammonia, NH3, chloride, fluoride, and well, let me do this one this way. Something like similar to acetate. And again, the R group's going to depend, that's going to determine whether we're talking about acetate here or one of the other, like ethyl acetate or something like that. All right, so it just depends what the R group's going to want to be. Now, the reason why all of these guys are falling into the fair category at this point, and we've got really in this list there are 2 different, really there's 2 different kinds. Maybe I could argue 3 different kinds of nucleophiles here. You've got the atomic ones, that's going to be these 2 guys here. And both of them are suffering from the fact that they're more electronegative than, say, bromide or iodide. So there's a higher charge density on a smaller atom, which makes these 2 things more basic. So now you have, competing reactions going on. This one over here, you have the fact that there are resonance structures here, right? This thing could be drawn this way. I'll just draw it really, really slowly. Which makes the alkoxy, that's this thing, a weaker base than like RO minus, all right? So structure and resonance here has affected the basicity, and so that means this is going to be a weaker nucleophile in the end. All right, and the ammonia is a similar situation because you have, you know, these hydrogens here. The nitrogen is not all that electronegative compared to like oxygen, for example. It's less electronegative than that, so it's a relatively weak nucleophile. And once it makes contact with an electrophile, you have this further issue where once this thing has formed a bond, I'm going to change my color here. The nitrogen now has a formal charge of +1 on it, which means that it's, and we're going to get into this in the next video, but this thing is now a good leaving group. So it makes this nucleophile not as good as it possibly could be. All right, and then the last, no, we got 2 more groups. So then the weak nucleophiles, and we've dealt with this again in the laboratory. In fact, you guys have experience with all of this. It may not have registered at the time, but we have. So in this category is going to be water, and then the alcohols, ROH. All right, and these are weaker nucleophiles. Part of it is similar to the argument here for ammonia. Once water or ROH reacts with the electrophile, there's going to be a positive formal charge on the oxygens, which means that these molecules can rapidly dissociate from the transition state that you just formed during the reaction. All right, and then the last category will be the very weak nucleophiles. And there's really only one example here. This would be like acetic acid. And you can see that we've got 2 kinds of oxygens in here. The carbonyl oxygen is not really going to be involved in anything nucleophilic, but the alcoholic oxygen here, the hydroxyl group, is what will be representative of how this is nucleophilic. All right, and because of resonance in here and whatnot, this also is going to be a super weak nucleophile. All right, now I think when you look over this video and you get to the point where we are here, we're going to be finishing. Once you've established all these categories and you've gone through the video, then what you need to do is step over here and think about how each of these factors, the basicity of the atom with the unshared pair of electrons, the amount of structure around it, and how the solvent could influence the nucleophile. And just to be sort of brief about the solvent effect, if you think about hydroxide here, for example, and if there is water in the solvent, then this thing is going to be strongly solvated this way. The water molecules are going to be flipped around in a direction so that the hydrogens are faced in towards the hydroxide. All right, and we call this a solvent cage, and there's lots of ways to think about this. I'm using the one that I think is easiest for you, where the partial charges on the hydrogen will be faced in towards the hydroxide, and this is going to have an effect on the ability of the hydroxide to get around, because it's essentially been caged off. And if you have an electrophile over here, for example, has a positive charge on it, this dude has to get over here. And if you've got it all bonded up with waters, it ain't going to be able to do that. So solvent effects, and we did a lot of different reactions. Some reactions we utilized what are called aprotic solvents. Boil that down to no water. And why? Because of this reason over here. All right, and we did reactions that were protic. we did a lot of condensation reactions that had H2O as part of the system. All right, so there are reasons to choose different solvents, and we're not going to get into all the intricacy of this right now. But I'm going to go ahead and conclude lesson 6, and we'll see you on the other side.